going to split up this talk in two. First I'm going to describe why we need low flow anesthesia, and then secondly why we need it to be automated. So there are several advantages to low flow anesthesia, and I think everybody knows about this. You preserve heat and humidity, and therefore you preserve heat. You reduce the consumption when you use lower flow. You use less of the agent because you re-inhale the exhaled agent. And you reduce the environmental pollution. I think everybody agrees about this, and there is, I think, very little actual discussion about the benefits of all this. There are consequences of reducing fresh gas flow. First of all, the difference between the delivered concentration and the inspired concentration becomes larger. First of all, I have to introduce the terminology that we're going to use. And we all have to agree that the delivered concentration is what comes out of the common gas outlet. The inspired concentration is what the patient inhales, what the patient gets. And the alveolar concentration is actually an indicator of the cerebral partial pressure, or the CNS partial pressure. So when we use low fresh gas flow, we can make these observations. There is a difference between FD and FI, between the delivered concentration and the inspired concentration. This difference is larger with more soluble agents. The difference is larger with low fresh gas flow, and it's larger at the beginning of the case. Another observation that we can make is that there is a difference between inspired and alveolar concentration. That difference is larger with more soluble agents. It's not larger with lower fresh gas flow, but it's larger at the beginning of the case. And the question is why? Again, these slides will be available to you so you can look at these questions more in detail and these observations. But I'm going to give you the quick answer. Why do we make these observations? It's because uptake and rebreathing. This is our anesthesia circle system. And when we lower fresh gas flow, we will have more rebreathing. In other words, more of the exhaled gas will be re-inhaled if we lower the fresh gas flow here. So the reason why the delivered concentration is different from the inspired concentration is because of rebreathing. And because the patient takes up agent in the alveoli, there is a difference between alveolar and inspired concentration. So the difference here is purely related to patient uptake. That means that the exhaled gases will have a lower concentration of your inhaled anesthetic than the inspired gases. And these exhaled gases are now re-inhaled. So that's why lower fresh gas flow rebreathing results in all these discrepancies between delivered concentration and inspired concentration. So reducing fresh gas flow results in more rebreathing, more dilution, as you would say, of fresh gases with exhaled gases, and obviously rebreathing of the exhaled potent inhaled anesthetic allows you to reuse the anesthetic, and that reduces cost. You could say, well, if we lower fresh gas flow, why don't we lower it a bit more? And then yet a bit more. Why can't we keep lowering the fresh gas flow? In other words, it's the same as asking the question, what is the minimum fresh gas flow that is required to keep our system going? How much do we have to administer? Well, our anesthesia system can be considered to be two reservoirs. On one hand, you have the bellows of the ventilator. On the other hand, you have the FRC of the patient. And what our anesthesia machine does is, based on these two reservoirs, we pump gas from one reservoir into the other. That's our minute ventilation. And we keep doing that the whole time. How fast we change gas from one container to the other, or reservoir, depends on minute ventilation. But that's really what it does. The inspired and the expired gases are diverted so that we can get rid of the CO2 through the CO2 absorber. But still we have this system where we have the two reservoirs and we keep pumping one reservoir into the other back and forth. In order to keep the system going, we have to have at least as much gas going into the system as that leaves the system. If more gas leaves the system, or reservoirs will collapse, and you have nothing to pump into one to the other reservoir. So basic question is how much gas leaves our system. That's displayed in this slide. Our average oxygen consumption by an adult is about, under anesthesia, is about 150 to 200 mLs per minute. And the other source of loss of gas from the system is the sampling, 150 to 200 mLs per minute by our multi-gas analyzer. Now, if that's your basic configuration of your anesthesia machine, your minimum fresh gas flow is going to be about 400 mLs per minute if you include some of the leaks in your system, which should be less than 50 mLs per minute. If you have a system where the sampled gases are redirected into your system, then your minimum fresh gas flow is going to be about 150 to 200 mLs per minute. You can't go lower than that. That's the bottom. So what are the consequences of lowering fresh gas flow? Initially, very high FDs settings are necessary because we have the time constant of the circle and FRC wash-in is longer with low fresh gas flow. And secondly, you have to compensate for high initial uptake. In other words, in the beginning of an anesthetic with a potent inhaled anesthetic, if you start off with low fresh gas flow, you have to turn up your FD completely. You have to turn up your vaporizer. During maintenance, you still need higher FD settings to compensate for patient uptake. But interpatient variability in uptake becomes more apparent when you lower fresh gas flow. I'm going to show that in one of the next slides. And people ask, well, does this reduce titratability? Well, not to a large degree because we can measure what we're doing. We can measure FA, therefore it's pretty easy to just dial to get the desired effect. Interpatient variability becomes more apparent when you use lower fresh gas flow and when rebreathing increases. And the uptake will affect the FD-FI difference, the delivered to inspired concentration difference. If you have more uptake by patient, the exhaled concentration will be lower than when you have normal uptake, and therefore you rebreathe more desaturated gases. Therefore, the FD will have to be increased. So there is a relationship there. We know that there is significant interpatient variability in uptake, and we have done that in a study that was published more than 10 years ago now, yeah? And in this study, we looked at the uptake of sevoflurane, and you just have to look at the black squares here, and you see that uptake gradually increases over time. Cumulative dose gradually increases, but the uptake rate actually lowers a little bit over time. But we see that there is a significant standard deviation. So we know that there is variability in uptake from patient to patient. Another study that we did, and that was only published as an abstract, was the general anesthetic equation of sevoflurane. What did we do in that study? Well, our target FA was 1.3% of sevoflurane in oxygen. And then we asked the question, what vaporizer setting is required at any fresh gas flow? So we went from fresh gas flows to 0.2 to 8 or 10 liters per minute, and we looked at the vaporizer setting required to get 1.3 alveolar partial pressure. And this is what we found. With high fresh gas, with low fresh gas flows, in this case 0.2 liters per minute, because we redirected the sampled gases back to the circuit, we saw that the vaporizer setting had to be initially 8%, but then it dropped off to 6%, and then it gradually decreased to about 5.5% to get 1.3 end tidal. 1.3 end tidal. So there was a huge discrepancy between the vaporizer setting and the alveolar partial pressure. It's a consequence of rebreathing, more rebreathing with low fresh gas flow. While with higher fresh gas flow, about 1 or 2 liters per minute, we saw that the vaporizer setting has to be about 1.9 to 2% for most of the time, a little bit higher with 1 liter per minute initially, but still about 2% to reach 1.3% end tidal. If you translate all these graphs into one curve, you develop a plane where you combine all these individual curves, and then you create a relationship between fresh gas flow in liters per minute time and vaporizer dial setting. And this is a graphic representation of the general anesthetic equation to get a target FA of 1.3%. What does that mean? If you start off here, and a lot of people start off with fairly high fresh gas flows, like 2 or 3 liters per minute. As long as your sequence of fresh gas flow and FD combinations remain on this plane, your alveolar partial pressure will stay at 1.3%. And now you can choose what pathway you're going to follow. You can follow any of these two gray curves, but you can follow any pathway as long as at any specific time your fresh gas flow is coupled with a specific vaporizer setting that is in this plane. Your FA will be 1.3%. This is what most people do. They stay at around 1 to 2 liters per minute. Initially, they use a little bit higher fresh gas flow to compensate for wash-in and initial high uptake. But they stay at about 1 to 2 liters per minute. But personally, I'm living up there. I start off with very low fresh gas flow from the get-go. I use very high vaporizer settings, and I gradually come down, and I stay in that plane purely by looking at my end-tidal concentration. So this is what I do. I start off with very low fresh gas flow, in this case slightly above half a liter per minute, 8%, and within a couple minutes I reach my desired concentration, and then I taper off my vaporizer setting to stay at my desired end-tidal concentration. The question comes up, if you do that, is that fast enough? Do you reach your end-tidal concentration fast enough so that you don't have a gap of awareness between the effect of your intravenous anesthetic and your potent inhaled anesthetic? And Michel has shown in this study that you don't need an opioid, you don't need a potent inhaled anesthetic in between your induction and intubation to deepen the anesthetic. You have plenty of time, 90 seconds, to do an intubation without any hemodynamic response. Based on that, after intubation, your patient is typically not stimulated for several minutes. So if you reach your desired concentration within 3 minutes, that is fast enough in my opinion. So the chance of awareness is basically 0. If we go back to this slide, we can see that we need high vaporizer settings when we use very low fresh gas flow. But that's not the whole story. If we look at the standard deviation there, we also need there is quite a bit of variability in the required vaporizer setting from patient to patient. Because a few minutes ago I told you that there is quite a bit of variability in uptake from patient to patient. And that leads to quite a bit of variability in a vaporizer dial setting that's required to maintain 1.3% alveolar partial pressure. So this is the direct consequence. The variability in vaporizer dial setting is a direct consequence of the variability in patient uptake. So there are a couple consequences of low flow. FA is not the same as FI, caused by patient uptake. FI is not the same as FD, caused by rebreathing. And both relationships vary over time because uptake changes over time and uptake varies from patient to patient. So the relationship becomes quite complex because of all this variability. So we need constantly varying FD, and we need a wide range of FD. And it's very hard to predict that from patient to patient what the required FD is going to be. Again, the FA will help you in steering that, but you cannot predict it. Before you start the case, you cannot predict what the FD pattern is going to be when you use very low fresh gas flow. Now, if we want to practice that way, how can we do that? How can we continuously vary FD, vaporizer dial setting, when we are busy doing all these other things? When we administer antibiotics after induction of anesthesia, when we place an A-line, a PA catheter, verification of placement of a double lumen tube, positioning of the patient, placing a TE probe, initial TE exam. How can we do all that? How can we constantly continuously vary the vaporizer dial settings when we are doing all these things. And that's what we have to do if we want to use low fresh gas flow. Well, so if you forget about the very high vaporizer dial setting at low fresh gas flow, you can gradually get into overdosing of the patient. Your FA will rise too much if you are distracted by all the other things that you have to do. So you have to really pay attention if you want to use this technique. Use low fresh gas flow from the beginning. The other option that we have is to start off with higher fresh gas flow, 1 to 2 liters per minute. And we know that if you use this fresh gas flow, if you set your vaporizer setting at about 2%, you will reach alveolar partial pressure at 1.3% relatively quickly. The problem with this is that your cost goes up because your fresh gas flow is higher than it really needs to be to compensate for uptake. So there is a better option yet, which I'm going to present to you later. Another issue is how good are we in clinical practice in reaching the desired FA throughout the surgical procedure. And to illustrate that we're not really very good at it, I'm presenting this study by George Mashur, which looked at the incidence of intraoperative awareness. So what did they do? It was a prospective study. The target of the potent inhaled anesthetic was 0.7 Mac. They did this in tens of thousands of patients, and they said, if we do this, what's the incidence of awareness? A fair study, I would say, especially because George Mashur is interested in the topic of awareness and post-op recall. However, the results were that the end-tidal concentration was greater than 0.7 age-adjusted MAC, a median of 84.8% of the time. In other words, 15% of the time they didn't reach the target that they intended to. This is a prospective study. They wanted 0.7 MAC of your potent inhaled anesthetic, and they failed 15% of the time. That's a very high failure rate, I would say. In other words, we're not really very good at obtaining the target concentration that we want, even when we know about it, even when we are very conscious about it. We're not good at it. So there is a better option out there, and that is to use an automated target control low flow anesthesia machine. It gives us all the benefits of low flow, cost and less pollution, and better humidification, and it's automated. The machine will do it for us. It's ideal. So these are all the benefits from, these are some of the benefits from automated target control low flow anesthesia. You have less cost because of less consumption. You set the target FA, you set the target FI or FaO2, and you set the target FiN2O or Fa, nitrous oxide. And there is controlled feedback from the multi-gas analyzer. In other words, the machine will take care of everything. You are not going to be distracted by your other tasks in order to obtain your desired FA. Currently, there are 2 anesthesia machines on the market. Pretty soon there will be more, but there is the ACES and the Draeger Zeus. The advantage of the automated system, again, is that the manual process is complex and we fail frequently. It's even more complex when you introduce nitrous oxide to the equation, and there is no distraction. You have a guaranteed FA control, which hopefully and probably will reduce the incidence of awareness. Algorithms define the FD and the fresh gas flow, oxygen, air, and nitrous oxide that will be used by the equipment. In addition, there is no chance for hypoxic FiO2. Older systems with an oxygen guard system do not always present hypoxic FiO2 when you use low fresh gas flow, and this is in the conventional mode. So we have to be careful when you use low fresh gas flow, because in certain situations you can develop a hypoxic FiO2, and your oxygen guard system will not prevent that from happening in 100% of the situations. So if we want to have a sudden increase in target FA, how is the equipment going to handle that? For example, if we are surfing at 1.3% N-tyl sevoflurane, and we change the target setting to 1.8%, for example, for whatever reason. How is the machine going to handle that? It can handle that in two different ways, or in several different ways. If the machine uses a vaporizer and you want a sudden increase in target FA, it may take a couple of minutes, even if you set your vaporizer setting to 8% in the case of Sevo. It may take some time to reach your new target. Whether the time is adequate or not is determined by the machine, by the algorithms of the machine. If the machine said, I want this new target within 2 minutes, not a possible 5 minutes, it will have to increase the fresh gas flow in order to get there. So if a rapid rise is wanted by the algorithm, then the fresh gas flow has to go up and the consumption will go up. To correct for that, for the increased cost that we see there, we should be able to set a time limit. We should be able to say, yes, we want the FA to go up from 1.3 to 1.8, but if we get there within 7 minutes, that will be okay. We should be able to set that, and then the machine will not have to increase fresh gas flow in order to achieve that new target. It will have enough time to do that. If you use an injector, there is no such limit, because you can give a much larger FD than 8%, which is the limit of the vaporizer. So with an injector, there is no such limit, and therefore you can achieve a rapid rise in FA very rapidly without increasing fresh gas flow, which is a very economic way of doing things. But the bottom line is the time to achieve the target FA should be adjustable. It is not quite the same for a decrease in target FA, because the decrease in FA, even if you turn the vaporizer or the injector off, the decrease will be determined by the pharmacokinetics. The additional factor that plays a role is the algorithms of the machine. If the machine thinks that you want this new target within 2 minutes, it will have to increase fresh gas flow to wash out some of the Sevo from the system. If we are able to change the time or set the time where we want to see this change happening, if we say we want to decrease the FA from 1.3 to 1%, but it's okay if that happens over 5 minutes, the machine will turn off the vaporizer, and probably within 5 minutes your new target will be reached. But if the machine thinks you want it within 1 minute, it will have to increase fresh gas flow, which means wasting Sevo into the atmosphere. So again, the bottom line is that we should be able to achieve the time to reach the new target. Similar story is true when you want to suddenly change the target FiO2 or FaO2, whatever the machine uses here. It's completely equivalent, so I'm going to go over this slide quickly. That automated anesthesia machines are more cost beneficial than conventional machines was shown in this study, where when you use a conventional mode with a fresh gas flow of 1 liter per minute, the cost is going to be, or the consumption of the agent and your gases are going to be higher than when you use target control anesthesia. So these machines are able to work in an economic fashion. The disadvantage of automated target controlled low flow anesthesia machine is that there is a cost associated with the equipment. So if the machine that you previously had is still working well, there is additional cost by replacing the equipment. If your previous equipment has extended its life, expected life, then you can simply replace it by this machine, and then there is not really an additional cost. But using lower flow increases the cost of the CO2 absorber, and that's a very complex issue that Jan is going to talk about later this afternoon. So why do I need to know about this? I think that automated target controlled anesthesia is the future of anesthesia. We'll go in that direction, whether we want it or not. This will happen. But it also changes our mind. We have all learned about the FA-FI curves from Ted Eager and how they rise and what the effect is of cardiac output and minute ventilation on the rise of these curves. If we use FA control, these curves are out the window. They are not valid anymore. And that is very well described in a study that we did using Gasman that Tom van Zundert published. So what are my expectations from such equipment? I want it to be accurate. There should be appropriate feedback from the equipment that you use. For example, there is one instance when the Aladdin cassette was removed from the equipment that the equipment went out of target control mode without really notifying the user completely. Also, I expect that the machine does some correct interpretation of events that are going on. We have an example where there was a cuff leak in the middle of the case, and the interpretation of the machine was that there was an increase in oxygen consumption. That is not a correct interpretation of the events. And finally, the ORCs, the oxygen ratio controllers, are still not really optimized in conventional mode, and we expect better from our equipment. And I would say that we expect feedback from the measured inspired concentration rather than relying on a kind of arbitrary mechanical system to do that. I want the equipment to use low flow throughout, but there are very few studies that have really looked at the true performance of these pieces of new equipment. So in summary, I talked about the benefits and the consequences of reducing fresh gas flow. I talked a little bit about automated target control low flow anesthesia machine. At least I gave you the basic principles of what these machines do. And the cost analysis is going to be extremely complex and will be discussed later today. Thank you.